For 38 years, one of NASA's most famous planetary flybys left behind a mystery nobody could fully explain, a magnetosphere so strange it made an entire planet look like it broke the rules of physics. Then, a team of scientists went back through the original data and found something genuinely unsettling. The spacecraft had arrived during an event so rare it happens only about 4% of the time, and it may have completely distorted everything we thought we knew about that planet ever since. Stick around, because I'm going to walk you through exactly what researchers found when they reanalyzed Voyager 2's decades-old Uranus data, why the original readings confused scientists for nearly 4 decades, and why this discovery is forcing a genuine rethink of what we actually know about one of the strangest planets in our solar system. And if you want more of these deep dives into real published research instead of recycled headlines, go ahead and subscribe now, because there's a lot more coming out of the far edge of our solar system. To understand why this reanalysis carries so much weight, you first need to understand just how limited our knowledge of Uranus actually is, and has always been. Voyager 2 remains, to this day, the only spacecraft that has ever visited Uranus up close. It flew past the planet on January 24th, 1986, gathering everything humanity currently knows about its magnetic field, its radiation belts, and the space environment surrounding it, all from a single flyby lasting only a matter of hours. No orbiter has ever been sent. No follow-up mission has ever returned. Every textbook description of Uranus's magnetosphere, the protective magnetic bubble surrounding the planet, has been built entirely on that one brief encounter, frozen in time since the mid-1980s. What Voyager 2 actually found during that flyby immediately struck scientists as bizarre. The spacecraft detected electron radiation belts around Uranus with an intensity second only to Jupiter's own famously brutal radiation belts, among the most extreme in the entire solar system. And yet, at the very same time, the rest of Uranus's magnetosphere appeared to be almost completely empty of plasma, the charged particles that would normally be expected to feed and sustain radiation belts that intense in the first place. That combination made no sense under standard physics. Radiation belts need a source of energetic particles to stay charged up, and Voyager 2's instruments simply couldn't find one anywhere in the surrounding environment. Scientists were left with 2 features that, according to everything they understood about how magnetospheres work, shouldn't have been able to coexist. If you're finding this as puzzling as scientists clearly did for the past several decades, drop a comment and let me know, because it genuinely helps me figure out what other space stories are worth covering next. For nearly 4 decades, that contradiction sat largely unresolved, treated as simply one of Uranus's many genuine oddities, alongside its bizarre 90-degree axial tilt and its magnetic field, which turned out to be tilted 59 degrees away from the planet's own rotation axis, an offset from the planet's actual center, by roughly a third of its radius. Uranus earned a reputation as the solar system's magnetic outlier, a planet that simply didn't play by the same rules as everywhere else. And the vacuum-like magnetosphere paired with intense radiation belts became one more entry on that growing list of unexplained peculiarities. The reanalysis that changed this picture came from a team led by Jamie Jasinski, a space plasma physicist at NASA's Jet Propulsion Laboratory, published in the journal Nature Astronomy in November of 2024. Rather than simply re-examining the moment of closest approach again, Jasinski's team took a broader view, going back through roughly 8 months of solar wind data surrounding the timing of the flyby, tracking the intensity of the stream of charged particles our sun constantly releases to see what conditions actually looked like in the days and weeks leading up to Voyager 2's arrival at Uranus. What they found was striking. Roughly a week before the flyby, solar wind pressure at Uranus's distance from the sun was unusually low. But in the days immediately before Voyager 2 actually arrived, that pressure spiked dramatically, increasing by a factor of roughly 20 compared to where it had been just days earlier. That solar wind spike, according to the team's analysis, is what actually explains the contradiction that had puzzled scientists for so long. When Voyager 2 encountered Uranus, the planet's magnetosphere had just been violently compressed by this unusually intense burst of solar wind, squeezed dramatically by pressure far higher than typical conditions at that distance from the sun. That compression event, the team concluded, likely drove existing plasma out of the magnetosphere entirely, explaining the strange, nearly empty vacuum Voyager 2 detected. At the same time, the same violent compression event would have intensified the dynamics inside the magnetosphere, injecting a fresh burst of energetic electrons directly into the radiation belts, temporarily, supercharging them to the unusually extreme levels Voyager 2 happened to measure during that exact window. Jasinski summarized the core finding about as plainly as a scientist typically allows, stating that if Voyager 2 had arrived just a few days earlier, it would have observed a completely different magnetosphere at Uranus entirely, one behaving far more like what standard models actually predict. According to the team's analysis, the specific conditions Voyager 2 happened to encounter occur only about 4% of the time, meaning the single dataset humanity has ever collected on. Uranus's magnetosphere was captured during a genuinely rare, atypical moment, rather than during anything resembling normal, everyday conditions at the planet. Linda Spilker, who worked as one of the mission scientists during the original 1986 flyby and now serves as Voyager's project scientist, has described the encounter as packed with surprises from the very beginning, and this new analysis finally offers a coherent explanation for exactly why some of those surprises never quite added up under standard theory. It's worth being clear and careful about exactly what this new analysis does and doesn't mean, because it would be easy to overstate the implications. This isn't a case of everything scientists thought they knew about Uranus turning out to be wrong. The reanalysis specifically revises how researchers interpret certain magnetospheric features captured during that one flyby, not every single measurement. Voyager 2 ever made at the planet. Jashinsky has been direct about this distinction, noting that the deeper, more fundamental issue this discovery exposes isn't really about Uranus's magnetosphere specifically, but about the basic limitation of studying any planet using only a single visit. As Jashinsky has put it, you genuinely can't tell the difference between typical conditions at a planet and conditions during an unusual, atypical day when you've only ever visited once. Knowing in advance that unusual solar wind conditions were present during the flyby would have prompted scientists to treat those specific readings with far more caution from the very beginning, rather than building nearly 4 decades of theoretical assumptions on top of what turned out to be a genuinely unrepresentative snapshot. That single visit limitation turns out to ripple outward into other open questions about the Uranian system that extend well beyond the magnetosphere itself. Voyager 2's original missing plasma. Observation had previously helped support a specific theory that some of Uranus's major moons might be geologically inactive, based partly on the apparent absence of material that active moons might otherwise be expected to contribute to the surrounding plasma environment. If that original plasma reading was itself distorted by a temporary, unusually intense compression event rather than reflecting typical conditions, then conclusions drawn from it about the moon's own activity may need to be revisited as well, an entirely separate scientific question that traces back to the exact same brief, unusual window of time. There's a related piece of this broader Uranus puzzle that connects directly to Voyager 2's radiation belt reading specifically, and it's been the subject of continued research even more recently than Jashinsky's original 2024 study. Follow-up work from researchers at the Southwest Research Institute has continued examining exactly how a solar wind structure known as a co-rotating interaction region, a specific kind of space weather pattern where faster and slower streams of solar wind collide and compress against each other, could have produced conditions at Uranus similar to disturbances more commonly observed and studied much closer to Earth. That continued research reinforces the same underlying conclusion from a slightly different angle, that ordinary, well-understood space, weather physics arriving at an extraordinarily inconvenient moment, is a far more likely explanation for Uranus's supposedly unique radiation belt behavior than any exotic, planet-specific property unique to Uranus itself. It's worth situating this discovery within the broader context of how much of our understanding of the outer solar system actually rests on exactly this kind of single, brief encounter. Uranus has never been visited by any spacecraft besides Voyager 2, and that gap in exploration is precisely why NASA's 2022 Planetary Science Decadal Survey specifically recommended a dedicated Uranus orbiter and probe mission as its single highest priority for the coming decade. A mission that would finally give scientists the kind of sustained long-term observation needed to distinguish normal conditions from rare, unusual moments like the one Voyager 2 happened to capture. That mission remains in the planning stages, with an anticipated launch sometime in the mid to late 2030s, meaning it will likely be well past the 50th anniversary of Voyager 2's original flyby, before humanity gets its next real look at this specific planet's magnetic environment. Hopefully this time, with enough continuous observation to finally tell the difference between what's typical and what's simply an unusual day. So what does all of this actually add up to? A 38-year-old mystery born from a single brief flyby that happened to occur during an exceptionally rare solar wind event has finally been resolved. Not through any new spacecraft or new mission, but through patient, careful reanalysis of solar wind data surrounding a decades-old data set that nobody had previously thought to examine quite this closely. Uranus's radiation belts and its strangely empty magnetosphere weren't necessarily evidence of some fundamentally exotic, rule-breaking planet after all. They were most likely the result of extraordinarily unlucky timing. A spacecraft arriving at almost exactly the wrong moment to see the planet behaving normally. That's a genuinely humbling reminder about the limits of drawing sweeping conclusions from a single visit to anywhere in the solar system. And it's part of why the case for finally sending a dedicated mission back to Uranus keeps getting stronger with every year that passes. If stories like this, one, grounded in real published research rather than exaggerated headlines, are what you want more of, subscribe to this channel and turn on notifications, because there's a real chance the next reanalysis of Voyager's decades-old archives uncovers another mystery hiding in plain sight, waiting for someone to finally look at it from the right angle. Thanks for watching, and I'll see you in the next one.